Before we dive into the basic skeleton creation, just one thing that I forgot to mention, that was the path setup, especially for USD building. If this was an actual project at this stage here where we are dealing with geometry, I would not only set the groups, but I would set the paths as well. So each different path will end up in a different hierarchy in the USD. So this will make easier to build different materials for each part. But since this is a very simple geometry, I haven't done that. But again, this should be an important and necessary part at this stage where we are dealing with geometry. So now let's start working with the base skeleton building. Here I change the visibility for this base part because we won't need that for joint placement. And this is what I said a couple of videos ago, where I think most tutorials online, they lack this speediness of SOP, of a custom SOP workflow. I feel that people are still doing things the same way as in other DCCs, and I'm against that. I think Houdini should be, well, a place, kind of operational system for 3D where we automate stuff. And as you can see here, this is my HDA for extracting centroids. And as you can see, it's using groups. It's getting actually the geometry groups, and it's automatically creating the name, kind of automatic, because it's based on this parameter. It's creating the name attribute for those points. Here, they are just points because they don't have the necessary attributes for that a joint needs. And as you can see, it uses the groups as the basis for getting the centroid where you put the point. This is kind of simple. It's just this. I'll have to. Probably there is some old parameter reference somewhere that is getting this error. Attribute promotes one. Yeah, oh, it's because of this. Not sure why it's getting this error from this part. I just let this here because I want to show you what I did, but this is not needed anymore. The basic idea here is a for loop that will loop this amount of times, and for each loop it will get the group that you set here. Let me show you. It's something like this. It's a blast where we are getting this part and then using an extract centroid for that. Unfortunately, the extract centroid doesn't accept groups. So it's set this way. It will use the whole geometry as the geometry for this bounding box calculation. And what I did was just this inside a for loop. That's what you can see here. So why I did this way using a compiled block? That's because if you have several joints that you are creating here. Every time you change anything on a parameter, it will drive the for loop to calculate everything again. So for just 4 joints, it's simple and fast enough. I'm not sure, maybe for 10, 20 joints, if that will start to make some kind of difference, maybe even more, depending on the skeleton. So because of that, I started to developing kind of a way to use attribute from parameters to drive the compiled blocks for that. So that's it. But anyway, I think for most cases, this will be enough. So that's the general idea. I think that since this is something that we won't change much, usually for this is just a kind of a one-time process where you create those points, and that's fine. We will start working on those points, so we won't be changing this so much. That's why I don't think having several of this makes much sense. Nevertheless, I don't think this is kind of a Houdini workflow, because Houdini is pretty good for automating this kind of workflows. Usually when I see this stuff on tutorials, I guess that the user is not so experienced in Houdini. Again, because Houdini has all those tools for automating these kind of repetitive tasks and avoiding have so many nodes. So here we have those four points. Yeah, again, there's 2 points here. Here I just did a small correction because those parts, I'm not sure, but they are not perfect, I think. And there is tiny error where you can see here this tiny difference. They should have the same, where is it? The same, this is, yeah, Z. They should have the same Z position. So this is just for correcting those. And this for correcting this X value here that was different. And here I added, let me see, some more joints. Here we have one for each piston. And here I just renamed those joints, as you can see. But it's not just a matter of renaming. I changed the position so they'll have the same position as the base of the whole this main part of the motor. And I changed the name. I call this piston underscore parent. This is this part here, this joint here. Oh, this joint here, this one. So, and I added 2 more joints. One will be the base, where we'll drive the transformation for, again, the main part, the base part of the motor. And another one will be the root that will drive all the joints, all the transformations. So just to differentiate those 2 transformations. You see why this matters later on. So here we have all those points, but they are not kind of joints yet, because for that we need some extra attributes. But before adding those attributes, I just did some kind of basic parenting using this parent joins node. So I think it's easier if I show you here. Where is it? Here. So we have the main joint as a parent for all the joints, then the base, then the parent, and then those two joints for each piston. It's harder to see on the viewport because we have overlapping joints. And here we have not overlapping joints, but we have overlapping polygons, overlapping lines. For this piston is easier because we have this parent, the base, and the top is, let me show you this way. Yeah, I think it's easier to see this way. For the capture, we don't need the actual joint attributes. We just need the names. And of course, the parenting, not for the capture package GU, but for nodes like capture biharmonic, because it uses this parenting to extrapolate the weights. So this is why it's important to parent your joints for your base skeleton before capturing. For the capture biharmonic, capturing using something like this, it's not a good idea. I will cover this later on after this introductory videos where we will rig a character, an actual character. So then we can talk more about the capture biharmonic. But I think there's a lot of videos on the internet about that because this is a pretty old tool. And here the capture use the names. You have to make sure you have the names on both sides, here and here. So for this, let's make sure here, what is it? On primitives, and here on points. So base, piston A base and top, piston A base and top, and the same for piston B. So we have the same names on both sides of the inputs. So that's why this is capturing all the geometry. You can see here that each geometry was fully captured by one joint or one region. This is they kind of use the same workflow, I may say, I think, from the old bone system that object level used. But anyway, this is working, you can see here. So now we have the base geometry for our skeleton. Of course, I can mention that here with the rig doctor, with this initialize transforms node, we have all the attributes that KineFX, let's say KineFX in general, needs for using soft geometry as the driver for animation or skeleton, again, in general. So here we have joints. And with that said, in the next video, we will orient those joints and we will create the guide skeleton if we have time. So if not, I'll split again the video just to talk about the guide skeleton. So that's it for now. I hope I see you on the next video.